section 8.1, the JFET specifically. I want us to go to the introductory paragraph. Let's read through there quickly just to give you some background. That's too much. Alright, it says there, BJTs, bipolar junction transistors, I hope you still remember them, were covered in the previous chapters. Now we will discuss the second major type of transistor, the field effect transistor. Field effect transistors are unipolar devices because unlike BJTs that use both electron and hole current, they operate only with one type of charge carrier. The two main types of field effect transistors are the junction field effect transistor, the JFET, and the metal oxide semiconductor field effect transistor, the MOSFET. The term field effect relates to the depletion region formed in the channel of a field effect transistor as a result of voltage applied on one of its terminals, the gate. But I will explain it to you just now. Recall that a BJT is a current control device, that is, the base current controls the amount of collector current. A field effect transistor is different. It is a voltage controlled device, that is, the base current. No, I'm at the wrong place now. It is a voltage control device where the voltage between two of the terminals, gate and source, controls the current through the device. But I will show you now in the next pages. A major advantage of field effect transistors is their very high input resistance. Because of their non-linear characteristics, they are generally not as widely used in amplifiers as BJTs, except where very high input impedances are required. However, field effect transistors are the preferred device in low voltage switching applications because they are generally faster than BJTs when turned on and off. Another device that we're going to discuss later on is the IGBT, and it's generally used in high voltage switching applications. So again, as we normally do, you can mark the introductory paragraph. The JFET, junction field effect transistor, is a type of field effect transistor that operates with a reverse biased PN junction to control current in a channel. Depending on their structure, JFETs fall into either of two categories, N-channel or P-channel. Now, if we go and look at figure 8.1, basic structure of the device, the same as we have seen with the BJT. Also a 3-terminal device, but the construction is different. I can see now I have also two types, N-channel and P-channel. I can see this is the N-channel. The N-channel has got a large piece of N-type material with two small pieces of P-type materials implanted in it. It's got 3 terminals, drain and source, and the gate terminal are connected to both of those pieces of P-type material. It's just drawn this way for simplicity's sake. But it will become more clear when we're going to discuss the basic operation of this device. P-channel again, I can see it's a large piece of P-channel material, 2 small pieces of N-type material implanted there. Also connected to the gate. Remember, both of them are connected to the gate, and also drain and source. Okay, that's the basic structure of this device. You don't have to be able to draw that. Just makes the understanding of it a bit simpler. Basic operation. Just below figure 8.1, you can underline this as this is very important. The JFET is always operated with a gate source PN junction reverse biased. Reverse biasing the gate source junction with a negative gate voltage produces a depletion region along the PN junction which extends into the N channel and thus increases its resistance by restricting the channel width. Let's have a look quickly how that works. There is a biased figure 8.2. The biased, I can see that it's an N channel because it's written there, and Here's my voltages, in this case called VDD because I have a drain, so it will cause me the drain to source voltage, and a VGG because of the gate. Please note that the gate to source voltage is reverse biased. That is important. And also I can see that it is a voltage controlled device. Alright, how does it work? We go and look at figure 8.3. They show us here the effects of VGS on channel width, resistance and so forth. What it basically comes down to, if VGG, which is my reverse biased voltage, for a specific voltage, you can see here that these depletion regions between an P and N-type materials grows. Alright? And I have a certain amount of current. But it will become more clear in the B section. You can see here that I increased VGG. I can see here that the current, the channel here becomes narrower, and because of the channel that becomes narrower, the current ID becomes less. Okay, so I can see as I increase the VGS, the voltage that is negatively biased between the gate and source, the two channels grows, and I can control the amount of current that flows through this device. On the last one there, again, I can see that VGS, when VGS is made smaller, the channel here becomes bigger, so more current can flow through, and I can also see it on the ammeter there that the current now increases. So you can already see by looking at these pictures that if I do not have any VGS applied to this device, in other words, no voltage is applied, you can already see that the channel will be open, maximum current will flow through this device. If I increase, but we will discuss it later again, if I increase VGS, the channel becomes narrower because of the depletion regions that's growing, and eventually the two of them will touch and no current will be able to flow through the device. Okay, that's the basic operation of the JFET. And of course the P channel will just be the opposite with the current flows. Right, the last paragraph there, it tells you the channel width, and thus the channel resistance can be controlled by varying the gate voltage, thereby controlling the amount of drain current ID, as we've seen in that figure. Alright, then of course we also have to know the JFET symbols, which is in figure 8.4. There's the symbols for the N channel and the P channel. Please note the difference, and you have to draw this clearly when you draw schematic diagrams using the JFET. For the N channel, the arrow is pointing inwards, and for the P channel, the arrow is pointing outwards. And you have to remember that, because also when you have to work with a circuit that's been given to you and have to do some calculations or draw some graphic analysis or whatever, which we will also discuss in sections to come, you have to know that you're working with an N channel or a P channel, otherwise you're going to do it totally wrong. So make sure that you do know the symbols for the JFET as well. Alright, so as you were told how to use this book, please do it. Get your money's worth. Read through the sections discussed. Make sure that you understand. Test yourself by doing the true-false quiz, circuit action quiz, self-test questions at the end of the chapter. And please do not forget the basic problems to do. If you can't do a basic problem, remember to refer back to the section, go and read again, and see if you can't clarify the work that you don't understand. And please keep up with the work. You see now how quick you fall behind with homework if you don't do it regularly. Alright, this concludes then section 8.1.